Yo, what's up, what's up? Welcome back. Today we're working on my x86 operating system. It's a operating system written for fun in Rust, and we're starting to see something come together. We have a operating system that when I build and run, it like builds this like ISO that's booted with grub, and it like boots in this virtual machine, QEMU. You see a bunch of logs coming out here. These are from writing to the serial console. QEMU is forwarding those to standard in and out. And we have like some form of like user input, right? I'm moving this paddle around in this game by pressing A and D on my keyboard. We're right into the screen, right? So this was like simulating a VGA monitor, and we were getting like visuals up. We have like a web server. If I open the right window, if I go to the IP address of this machine, we've got like a rudimentary HTTP server, which requires like TCP and HTTP and like address resolution and Ethernet, which is done over PCI. So we've got like a bit of a driver stack started. If I like punch something in here, we do see that thing come back. So the server is like processing that, and it's not doing anything with that data right now, but like we could do something if we wanted to. It has like multi-core, so each of these CPU requests are each of these HTTP requests I refresh are being serviced on whichever core is available, which does change occasionally, CPU 1, CPU 2. We're using like Rust's feature mechanism pretty heavily, so that gives us a lot of like the concurrency for free. And what we're working on right now is USB. So the idea is this guy on the internet, he said, does it run Doom? And I was like, fuck, man, it doesn't. This guy beat me. He hit me with critical attack. I need to fix that. And so one of the things that I'm missing there is mouse. And there are like a couple of mouse mechanisms. There's this like PS2 mouse, which might give me a mouse for the PlayStation 2, but that's not what I mean. What I mean is the port here is like a serial port that the mouse plugs directly into, and that's how we implemented keyboard, is we use this like PS2 keyboard. But in my mind, I'm like, I've literally never seen a PS2 mouse in my life, but I have seen a PS2 keyboard, so that's how I kind of justified that. Probably not for like the last 10 years, but I have seen one. And so what I wanted to do is I wanted to do USB mouse support, because that seems like more realistic and like a better path towards real hardware at some point in the future. And so what I'm going to do instead is I'm going to implement like a USB stack. Wonderful. And so what we want to do there is we've implemented something, right? We have, in the past few streams, we've gotten to the point where USB is working to some extent. So the mechanism we have right now, here is my computer, CPU. He talks to a like PCI card. And I think, if I understand correctly from the spec, every single USB card is like a PCI card. So we go through like the PCI bus, which is connected to my like USB card. USB host is what they call it. Now, there's a lot of protocols here depending on if you're on like USB 1.0 or 2.0 or 3.0, but we're starting with USB 1.1. So we're looking at UHCI, which is like Universal Host Controller Interface. And so the idea is we implement like the host card implements this spec, we implement this spec, and now all of a sudden, if you like swap out the host card for a different one, like an expander or whatever, it should still work. We also have like, we're also connected to like memory. So we have like RAM going over here to the USB card as well as to the PCI bus. And so how it works is like, we talk to the USB, we like enumerate the PCI bus, we find the card, we then find like where the address of this card is in our memory space, and then we talk to it. I'm kind of oversimplifying. There's also like this thing called like IO space, and I think we're using like IO commands, not memory commands, but the same line, so it's essentially the same thing. We have like these like addresses that we can write to like interact with this guy. We'll have like a little mouse plugged in here. Here's my mouse. And what happens is we send messages out from the host over the USB port over the bus. that will request something from this mouse. So the idea is he plugs in, he says, hey, I'm a new thing that's plugged in, or the card notices. He goes like, oh, I know somebody's plugged in here. And he says like, the new thing that's plugged in, he's got a device address 0. We are going to configure him to have like a device address of some other number. And then we'll like send out packets on this line. And we'll say like, you know, you might have like a keyboard here too. That's what a keyboard looks like. And, you know, each device on the bus, well, they'll all see the same packets. But depending on who the host is talking to, the mouse or keyboard will respond. Something interesting to note here is that the mouse can never initiate a transaction with the host. All the mouse can say is, I would like you to poll me as fast as you fucking can. And so then the question becomes like, okay, so how do we do stuff like at some frequency? And the UHCI card, I think that this is a UHCI detail, not a USB detail. There's an important, we have to just make a distinction between those because a lot of the USB stuff is applicable for all versions, but UHCI stuff is only applicable for USB 1.1 cards. And so the idea is that this guy has like a list of things to do. Here's his list, right? Maybe I'll stop drawing dotted lines. And what's weird here is each of these things are iterated through at a fixed rate. So the card will like start here, and after 1 millisecond, he'll go here, and after another millisecond, he goes here, and after a millisecond, he goes here. And so what you can do is each of these guys points to like some work to do or a queue of work to do. And so what like this book I read, what's it called? I should reference it because it's very helpful. The Universal Serial Bus Book. This guy. So this book, he explains in it that what you might want to do is if you're, sorry, let me find the right window. If you're like trying to pull at a certain frequency, you might have like every fourth one of these ones point to Q4, right? So like which is like the period. And then maybe here you have Q4 points to Q1. So like there will be work to do over here, which points to like work. This guy also points to like other work. And so what happens is like every fourth frame, he'll like iterate over the Q4 work, and then he'll iterate over the Q1 work. And then from each individual one, you also point to Q1. And so what that does is like it kind of like allows you to schedule work by just having the card automatically iterate over these things. And so what we did last stream was we kind of got to the point where we made a queue of work, and we didn't like do any of this like fancy scheduling or anything. All we did was we said, could you please tell us what you are? And so we like, and once you're done, we just like unscheduled all work. And it turns out that we did that correctly. However, we weren't sure at the end of last stream what was going on because we're taking a lot of shortcuts. We're like far from complete here. But what we see here is we schedule some work, and the work is at this address, and we say, oh, here is like what the work scheduled is to be done. We wait 2 seconds, and then he says, oh, there's no more work to be done, which proves to us that the hardware is like enumerating our list and doing work. And we got this buffer back. We called like, hey, this thing called like get descriptor. And we said, hey, mouse, could you tell us what you are? I guess we don't know it's a mouse. We just said, hey, USB device that we see, what are you? And he returns back this buffer. And we were kind of struggling at the end of last stream because, sorry, I keep opening the wrong Firefox window. I want this one. Let's look at the USB OS dev wiki. It's been kind of slow recently, so give it a sec. Come on, please, please. Oh, come on, we can get there, buddy. I guess I can look up like a backup. Oh. It's so close. USB. There we go. Okay. We'll just try not to close this. But we looked at like the response for this get descriptor, and we saw like, oh, the size of the descriptor, the device type, BCD, device class. Sorry, this is like the USB spec version, subclass. And we were looking at things like this, like USB specification release number, which should be an offset 2 and should be 2 bytes long. And it should be in binary coded decimal. So we should see like something like 2.0. But we're saying like 0.2, which is like kind of odd. It doesn't look quite right because there's no USB spec 0.2. And so we were just kind of confused about like the endianness of the response. So when we see these like 2-byte things, they're actually in little endian ordering. So this should actually say 2.0, and all of a sudden that makes a lot of sense. So what we want to do today is we kind of want to like build on this. We've sent this request, got a response of like, what are you? And then we want to start like using that to kind of dispatch to a mouse driver maybe, and figure out like, what does it look like to poll this mouse at a frequency, like a certain frequency, and like how would we set all that up. Yeah, so that's the goal today, is just to make some form of progress on like getting information from the mouse. Yeah, so I think the first thing we want to do is we want to like actually probably parse this correctly. So we'll say parse device descriptor correctly. And then from there, we're going to want to like start figuring out like, well, if we get the response, like how do we use that to dispatch to the correct driver? How do we know if it's a mouse? How do we understand that? How do we work with a mouse if we get it, etc. Yeah, that's the goal. That's the goal. Yeah. So we'll say that we got ready for this at like 11:30 into the video. Okay, so where were we yesterday? We looked at this like get descriptor function. We created this like setup packet that we kind of referenced this guy's GitHub from his USB book, and we allocate this read packet. And we say like, hey, I'm gonna ask you to give me some data back in this read packet. And then what happens is we set up this thing called like a transfer descriptor, which is our like smallest unit of work. There's queues and transfer descriptors. Each queue points to multiple transfer descriptors, whatever. And we say, hey, transfer descriptor, please send this USB setup packet, which is like a USB level protocol. Remember, there's like USB and then there's host control, like USB host. So in USB, the device should get this like setup packet. And then it expects the next thing for us to send is like a read packet. So we say, please give us this information, and then after that, please respond to that request in this buffer. So that's what this read packet is. Then we say, in our setup, we say, hey, the next thing that you're going to do is do this read thing. So we set up our read work, which is, there's some details here that we haven't quite figured all of them out yet. And then we set up our setup request, and our setup request points to the read request. And then we put both of those guys into a queue of work. And so like the queues in USB, they'll auto increment themselves kind of. So like you point to the head of the queue, and when it executes that unit of work, it'll look at this like link pointer inside and be like, what's the next thing you want to do? And he'll automatically update himself to do that next thing. So if we queue up multiple things of work to do, all we have to do is wait for the card to finish those. So we wait for that to finish, and by wait for that to finish, we actually just wait 2 seconds and hope that it finishes in 2 seconds. Of course it will, but really there's probably something that we're supposed to poll to figure that out. And then we read it back. And so I think the first thing that we want to do is like create some sort of structure that will read that back, as well as fix up something here. So one is that the reference that we're using, we were looking at, is like this GitHub link to... let's see if I can pull it up. This guy, and he did this thing where he gets the descriptor once but only pulls the first 8 bytes, then resets the port, sets the address, and gets all 18 bytes. And that's like kind of like this like weird trick that he's doing because in his book he says some devices will not respond with the full 18-byte descriptor unless their address is set. And maybe you're not supposed to, like, for legacy reasons, I guess, he's doing this so that he's compatible with more devices. But I say, fuck them. I'm going to do what I want, and I'm going to come back and fix this if I ever encounter a device where that's a problem. But in reality, that won't happen because we'll never get very wide usage of this operating system. And if we do, we can revisit then. So something we have to do here is we have to set the size. So this is a little endian thing that says number that says how many bytes do I want to read. And so I want to read 18 bytes, which is hex 12. 16 plus 2 is 18. And because that's the size of the like standard descriptor. You can have extra stuff in there if I remember correctly, but really we should just say, fuck it, just give us the standard descriptor. Which means that our red packet has to be 18 bytes long to get the response. And here we need to say, hey, USB host card, if you get more than 8 bytes, please like stop. I'm pretty sure what this says. Let's just double check. If I set like the maximum length of the descriptor. So I can say like, hey, host controller, here's a buffer and here's some stuff to like, I'm put the response of the USB device in this buffer. But then we can also say like, hey, the buffer that we gave you is actually only 8 bytes long. So don't fill it all the way. So you need to both ask the device itself for 18 bytes, as well as allow the descriptor or allow the host card to put 18 bytes in our buffer. So that's 3 spots where we had to set that. 1 in the packet, 1 in the size of our array, and then once in the like descriptor for the controller card. And so if I do that, we should see like an 18-byte buffer. Let's take a quick little peek-skis. We have to wait 2 seconds, which is probably wrong. And we are seeing like data fill the whole thing, which is good. And so now we can just start looking at the format of the response and trying to put it together. Well, so probably what we're gonna do here is, this is like a kind of workflow that I've started using when I'm working with like data sheets that define layouts of things. We can say that we have a thing and it's a USB device descriptor. And he has like some amount of U8. He just takes in a U8 buffer. Because we don't want to actually like copy any data here. We just want to like look at it. And we'll write some functions that will like get and set, or maybe just get values from this descriptor. In reality, we could do setters as well, but for now, let's just do getters. And I'm just gonna like paste all of these guys here. So these guys have their offsets. I wonder if I can like make a macro that says delete everything I don't care about, which it looks like I can. So this is just Vim repeating some actions that I did before. Oh, actually, I do care about the number of bytes that it is as well. This is actually saying this first field is the offset, the second field is its name, and the third field is its number of bytes. So I guess I actually want this to go away. Because then we can use these numbers later to automatically generate functions. Okay, so I'm going to convert each of these guys into a function. So we'll say, so what does this look like? We say like function length takes in self and returns a U8. This is 1 byte. And how are we going to use these guys in here? So we're going to say function, this guy, takes in self, returns a U8. I guess then we're going to stub out his function. And we're going to say self 0 at something. And we're going to say to something else. So I guess this is going to be thing plus 1, plus the number of bytes that we want. And then we're going to say, I guess that's all we're going to macro out for now. And then we're going to say, put in this guy here and here. And I think that's enough. Ah, fuck. The macro didn't replay correctly. That sucks. I was too hopeful. Maybe here. Ah, haha. Okay, So if it's because I started at the beginning of the line. Look at that. Look at that. Okay. So that seems reasonable. And then we just have to fix some of these return types. So anything that has a +2 should be a U16. So that's this guy, this guy, this guy, this guy. Cool. And then these guys that return U16s. I guess anybody that returns a U8 actually shouldn't have the +1 in here, so we'll just delete those. Right, because each of these guys already just return 1 byte. Okay, and then anything that returns a U16, we just have to convert it into a little endian parse. So we'll say U16 from LE bytes. And then we have to say that this slice needs to be converted into an array of size 2 that it knows at compile time, and we'll say failed to convert to 2-byte array. And it looks like it accepted that. So now we just go to each of these places and rerun that macro. And now it looks like we're compiling and we just have like warnings, I think. Cool. So maybe we'll just cargo format real quick because that'll fix some of these like spacing issues. And now we just have to set these names. So this will be length, descriptor type, BCD USB version is what this field is. We'll call this device class, device subclass, device protocol, max packet size. I wonder, 0. So we'll just say endpoint 0 here. Vendor ID, product ID, and then what's this BCD device? Device release number. Device version, we'll call it. Manufacturer. String ID, I think is what this is, if I remember correctly. This is I manufacturer, index of the string descriptor describing the manufacturer. Yep. Product string ID and serial number ID. Sick. Okay. So now we have like a bunch of functions that we can use to read this. And so I think what we want to do is also we just want to implement a like debug logger for this. So we'll say use create or core format, and we'll say impl format debug for USB device descriptor with any lifetime. We don't really care. And we say, what do you want us to put in here? And it's this guy. And so now I think all we have to do is just copy paste all of this. Take out anything that isn't a function, that doesn't have the word function in it. So we say anything that doesn't have the word function in it, delete it. Cool. And now we can just like convert these into string writes. So we say write to this formatter, and we call length, or we like paste the function name, and we probably print it in hex, and the argument is going to be self.length, and we delete the stuff in the brackets, and then we finish off that write. And so I think I can just do that for all these. And I guess each of these guys is going to have a comma at the end of him, because these are going to be like part of a array of things. And we'll just say write to this USB device descriptor And here we'll close the bracket. All right. Okay. I think that's good. And so now we can, when we get the device descriptor, we can stick this guy into our USB device descriptor like this, and we'll get the debug output of our new struct. And hopefully it looks reasonable. Yeah, nice. So we say we read this descriptor. He's got length 18, which is 12 in hex, USB version 2.0. Great. Device class 0, subclass 0, protocol 0. Okay. Max endpoint size, max packet size for endpoint 0 is 8 bytes. Vendor ID 627, product ID 1, and these are hex. And we actually can confirm if we look at the QEMU source code. We can find the definition of the USB tablet that we're punching in. Just let me double check where it was. I think that it was this guy here. This guy. There was somewhere where I found it before. USB tablet properties. I swear I found the use of this somewhere. I saw like the vendor ID and the 0x0627. I swear I found, yeah, I did find these. I don't know how I found them before, but here we go. We have like this tablet descriptor, and we see the vendor ID is 6287 and the product ID is 001 and the device version is 0, and that matches up what we see here. We see vendor ID 627, product ID 1, and device version 0. Great. Were those generic fuzz configs fuzz tests or something else? Sorry, where are you talking about? I don't think I was fuzzing anything, unless you're talking about what I was grepping in the QEMU source code. I wasn't really reading very closely. Could have been anything. But yeah, it looks like we have a device descriptor that's like pretty reasonable. So pretty cool. Oh yeah, so here I was probably grepping for the term USB tablet. And yeah, it does look like they have some sort of like, generic fuzz configs. Yeah, it does look like they had configs in QEMU for fuzzing something. I don't know. Yeah, I'm just grepping all of QEMU. Who knows what that is? Probably somebody does, but not me. Okay. So what am I looking for now? So we have a descriptor that we've got from this guy. And so presumably we should like do something about that descriptor. But before we do that, I'm just remembering that we're violating the USB protocol here. So we're doing like a setup transaction followed by a read. But if I remember correctly, we also have to ACK the read so the device knows that it can like finish. Because I think like the device might be like in this state where it's like, oh, I'm sending this thing out. And did it get it? If he didn't get it, I might have to resend it. So he's like sitting there waiting, and so we just have to be like, hey, don't worry, we saw it. Where did I see this? Setup, data 0, ACK. So we need to send this ACK. And if I remember correctly, an ACK handshake is used to communicate that the data packet was successfully received without any bit stuffing or CRC errors over the data field, and the PID packet was not corrupted. ACK packets may also be issued when receiver's sequence bit matches the sequence bit of the received data packet, blah, blah, blah. ACK packet may also be issued when the receiver's sequence bit does not match the sequence bit of the received data packet. This may seem counterintuitive, but the reasoning will become clear in the sections discussing data toggling. So what does this packet actually look like, though? What goes in here? Yeah, I don't really see, if I remember correctly, it's just like an empty packet. We can probably go to this GitHub of this guy, and he's probably done it right. This book author. So here, he puts somewhere here, he puts this guy at the end, which is a output packet, which is claiming, hey, I'm a write, but he's got no data in him, is how he's structured it with these parameters. The other thing that we have to do today actually is fix our transaction descriptor generation. So we've been like reading this guy's stuff, and he's got a lot of like manual bit shifting, and we've been converting that into like human readable words. But we didn't implement the second word of the transaction descriptor. So let's see if I can find that somewhere. Probably that's going to be in the like Intel UHCI spec PDF or something. I want UHCI. Why are you giving me EHCI? God damn. So here, when we were generating these descriptor functions, we were looking at these and going like, oh, this second chunk of data is host controller read write. So we probably can just leave it 0 initialized. And it seems like from the reading, like this guy's example code, that's not true. So let's maybe do that where we'll implement read write, or we'll implement like the correct writable fields here, and then we can like see what he's actually doing. So let's do that. We'll say maybe at like 3130, we're looking at implementing td control and status reg getters and setters. Okay. So somewhere we have our transaction descriptor. Transfer descriptor. I get this mixed up all the time. Transfer descriptor. And here we probably just have to set these values. So these are all working on word 2. These are working on word 0. So probably the new functions go in here. And we just start writing them out. So we say short packet detect. This is at bit 29. So we'll say function set SPD. He takes in self by mutable reference, and he takes in a value that is a Boolean of what we're going to set. And we just say self 0 at word 1, the second word in the control structure, and we say set bit 29 to whatever the value that we try to set it to is. This field is a 2-bit down counter that keeps track of the number of errors detected when executing the TD. If this field is programmed with a non-zero value during setup, the host controller decrements the count and writes it back to the TD if the transaction failed. If the counter counts from 1 to 0, the host controller marks it inactive and sets the stalled. So I guess if we like fail to write the same thing over and over again, we just give up, and we'll just leave this as 0, I guess. But I guess we can like set the value. So we'll say function set. I guess before we move on, actually, I do want the ability to I want to unit test this to make sure that our like parsing is correct, since we're doing setters and getters. And we can just say this is a get bit 29. Yeah, sure. And then somewhere we have these like transaction descriptor tests, and so we'll just say test SPD, and I guess all we're going to do is we're going to make a transaction descriptor. We're going to set his SPD to something true. We're going to test that the thing that we set results in bit 29 being set. And then we're going to test that if we get it back, we see the same thing. Wonderful. Argo test. Just double check that real quick. And do we see test TD SBT passes? So we're chilling. And now we just do the same thing for these guys. So this is error counter, I think. Yeah. So we'll do the same thing for error counter. This returns a U8, and he takes in. So he gets bits 27 and 28, so 2 bits from shift to 27. And here, when we set it, we need to make sure that we don't set it to anything greater than 3. So we say assert that val is less than or equal to 3, and then we say set bits 27, 2 bits shifted by 27, we set them to this value. Cool. And then we just bang out our unit test here. So we say SPD, we replace all of these SPD usages with error counter. We assert that this is 1, 1, shift left by 27, and then this is, if we set this to 3. And we make sure that when we read it back, we get the same thing. We run our test real quick. Hopefully it passes. It's easy to make a mistake with this type of thing, so let's get a double check. Yeah, we fucked up, so at 760, it's because I wrote 1, 1 instead of 3 here, because I was thinking of Boolean, not in decimal. So let's just double check again. There, now everything's passing. Great. So data format is bits are being written to the right place, and we're seeing a getter and setter come back. What's next here? Low speed. Okay, so here we do the same thing. We replace SPD with low speed. Replace the 29s with 27. Oh, was it 27? 26. And we make a test for low speed. So we replace SPD with low speed. This 29 is a 27 now. 26, sorry. And probably this test will just pass for free because it's very simple. Yep, easy peasy. You know, you could argue that like all of this stuff is so it's so repetitive that you could implement this with a macro, and that's probably what this like bit fields Rust crate does, if I remember correctly. Is like you can define a struct in a macro where it will automatically generate these getters and setters. But fuck it, I don't really mind. I don't mind for now. Okay. So what's the next one? Isochronous select. Chronous select. And 29 is replaced with 25. And we make a test for this. Which says replace low speed with isochronous select. And this is bit 25. Give it a sec. Bing, bang, boom. Yeah, working fine. What's next? Interrupt on complete. Copying this guy because he's very few letters. Pasting him down here. Replace SPD with interrupt on complete. And 29s get replaced with 24s. And here we replace isochronous select with interrupt on complete. And we replace this 25 with a 24. Womp, womp, womp. Cool. And there's only a couple more. We have the status. which should probably return an enum of some sort, but for now we're just going to return the U8 here. So this is 16 to 23 inclusive is an 8-bit field. So we'll say function, what is this guy called? Status, returns a U8, and this is self, the inner thing, the first word, get bits 16, shifted by 16, and 8 of them. And the setter should be a value of U8. He sets the bits to value as 32 because it needs to get cast for this thing to work correctly. And there's no return. And this needs to be mutable. So we'll just quickly test the, this is test status. We'll set the status to like 0x, I don't know, EF or something. We'll test that the status bits are set to 0x AF, shifted left by 16. And then we make sure that when we get the status, we get the same thing back. Come on, baby. And easy, no failures, we're chilling. These guys are reserved, and then we just set the actual length. So what is this? Actual length field is written by the host controller at the conclusion of the USB transaction to indicate that the actual number of bytes were transferred. This can be used by the software to maintain data integrity, so we don't read like garbage data at the end of our buffer. Cool, cool, cool. So we'll say actlen is self, returns a U16 because this is 10 or 11 bits, which is more than 8. We say, please get the bits, 11 bits starting at offset 0. And then we make a setter. So this guy takes himself by mutable reference, that's a value. And this guy says set bits to val. And then test td actlen. And I guess here we should assert that the value is less than 1 shifted left by 11. Yeah, because bit 10 is valid, bit 11 is invalid. Cool. Cool. So here we say set actlen to 0x, I don't know, FFF is 12 bits. So we'll just pick like a smaller number here. I think that's fine. So then we test that this is equal to 5FF, and that if we get actlen, we see 5FF. I think that that's great. We'll see. We might assert here if I've put too many bits in. Nope, looks good. We are chillin'. Actlen test passes. And so now like the last thing to do is I have a test in here somewhere where we like manually constructed one of these things, and we just want to make sure that all of these guys that we just added are correctly parsing these as well. So what did we have? We had SPD, we had error counter, we had low speed, we had isochronous select, interrupt on complete, status, and actlen. So bit 26 is low speed. So low speed is true in this case. We have something shifted left by 27, so status. So, or the error counter should be 3. We have something shifted left by 16. So that's the status. status should be 0x80, which makes sense because the active, we need to set the active flag for this to process at all. I've set to 1 by software to enable the execution of a message transaction by the host controller. When the transaction associated with this descriptor is completed, the host controller sets this bit to 0. So what we're probably going to end up doing later is we're going to set this to 1, send it out, and then poll it to be for 0 and see if it ever finishes. Which means that this status should be 0x80, and everything else should be false that we just added. Let's see if that still passes. He doesn't like that because our actlen, we tried to set false, which should be 0. Bada bing, bada boom. Everything passes. We're chilling. Okay. That was a kind of boring 15 minutes, but it is what it is. You gotta punch some stuff out sometimes, you know? Which means that now we can go back into these places where we're writing these guys and we can see what he's actually doing. So we're setting low speed to true, right? Because low speed was bit 26, if I remember correctly. Yep. We're setting error counter. He's setting it to 3. I'm just gonna set it to 0. Fuck it. I don't really care. And we're setting the status to 0x80. That's important. Setting the error counter to 0, we can actually like assume we don't need to do because we've 0 initialized everything, so we'll just take that one out. And so we'll just add these to this guy here. And I think set low speed also probably isn't required. I think this isn't a low speed device. I think actually you're supposed to read the port descriptor from the UHCI card, if I remember correctly. Dude, DuckDuckGo, come on, man. Like, none of these, you're not going to give me the one I want. It's so stupid. Universal host controller interface. Wow. Is it really not getting it? Is it universal host controller interface? That's crazy that it's not getting it. And it's like going through this OSDev wiki is going to be so slow. I don't know why it's taking so long. See also UHCI. Like, come on, DuckDuckGo. You could have found that shit. Okay. So I guess let's cargo run this to make sure that those changes I just made to replace the like bit manipulation with these like named things still result in a thing that's being read. And we still are, oh, that's not good. So whatever we just changed made it not run. We just didn't get what we wanted to get. So it's because here, I was using the read TD instead of the setup TD. So I only set these on some of these guys. Big mistake. Big mistake. There we go. So this looks like it's still working correctly. Specifically, we see the vendor ID, product ID that we wanted to. Wonderful. Wonderful. Oh yeah, so what I was saying before was that I was supposed to read this port status will tell me if it's low speed, and if it's low speed, then we should set that low speed bit. But I'm just ignoring that for, I shouldn't. I don't know, maybe I'll come back to this later. Maybe we'll assume that everything is low speed for now, and then come back to it. I don't know, we'll see. We'll see. What's the next thing that I want to do? So right now, I'm kind of like allocating these like descriptors on the stack, and then punching them into this queue head that's also on the stack, and then when I send those out, let me think. These are like not in a good place in memory if we're going to be using like, if we're going to be able to queue up stuff on the go. So probably the next thing I want to do here is make a like better queuing system. So specifically like when I put things on this host controller card, I guess I need some way to associate drivers with how do I say this? Sorry. There's going to be some form of service loop probably that polls descriptors to see if they've been completed. And when they've been completed, it should dispatch those to the driver that sent them, right? So if I'm a mouse driver, I'm going to say like, hey, I want to send this setup request to figure out what the fuck is going on with this guy. And I need to at some like find that thing has completed and send it back. But maybe that's a job for later, right? Because right now we're still working on like initialization of the devices at all. Definitely what we have to do is we have to set the address of this guy. So how do I want to handle this? Maybe what I do is I move all of these guys into like heap allocated memory for now. Stick them like in the driver so that the driver keeps track of them. And then once I see them be completed, then I can like free them. So here in my UHCI driver, I'm probably just going to say like TDs is just a vector of boxes of transfer descriptors. Now, I would normally, like, my first thought here was to make it a vector of transfer descriptors, but if you do that, then you're in this, like, shitty situation where, how do I say this? When the vector is, like, reallocated, like, this, the pointers to these guys will move, and we need them to be in, like, a static memory location. So we're going to do it this way. We need to import the box type. For our like unique pointer shit. And we'll make another one that's like queues is a vec box queue head. Great. So now these guys all have like stable memory addresses. And now what do we do here? We say we make our descriptors. Great. But they need to be boxes. And I guess the packets that are associated with them also need to be stored somewhere. So what are we going to do with those? Maybe we make a, like, we have like transfer descriptor storage that associates the vector with the transfer descriptor. So we could maybe have like struct td storage transfer descriptor storage, and he's going to have a buff, which is a vec of u8, as well as the descriptor. That seems reasonable. I wonder if it makes more sense to do this at like, you could also do this at compile time, maybe, where you like put in like n is a constant here and allocate it directly, but I think it's okay to have the double indirection, and I'm not really worried about it. And then, so in our UHCI driver, we're going to store not just the transfers, we're going to store heap allocated pointers to transfer descriptor storage. And what's kind of nice here is the alignment should all just kind of work out. Because the transfer descriptor storage has a descriptor in it, then it knows that the descriptor has to be 16-byte aligned, and so it'll like probably do something intelligent to figure that out. And so now what we can do is we can say self storage or self TDs push box new T transfer descriptor storage, and this guy is the read. He gets the descriptor as the read TD, and the buffer as the read packet. So we have to be very careful here, because now we're kind of in this problem where like things are moving around, and we just have to make sure that we're like very careful about using those memory addresses correctly. So maybe how do we want to do this? I'm trying to think if like vectors of these guys are really the storage type that we want. Maybe we want like indexed things that have IDs, right? The idea could be that you like reference this specific transfer descriptor later. Not sure. Not sure. I guess for now, we will. Is this like what you're supposed to use pin for? You're supposed to have like box pin. Which will create a pin box T. Then X will be pinned in memory and unable to be made of constructing and pinning of the box, and also be done in 2 steps. Pin boxes is the same as box into pin. Right, so like the idea of like a pinned thing is like this guy knows that he's in a static spot in memory, which could probably help us out here, but this doesn't help us with the ownership problems here. Okay. Let's do it this way. So instead of using a vector here, I think I am going to use a hash map. The idea is that I want like IDs that are static and will not change, that are associated with the transfer descriptor. And because I'm thinking of like a scenario in the future where we have like our USB driver, like so we'll have like our mouse driver, and he'll probably talk to like a USB driver who will like create like, you know, I'll say like I want a setup packet, and he'll probably talk to the UHCI driver later, and he'll probably have a like push packet. And maybe I'm gonna have some form of way, like if I push the packet and the packet returns like a packet ID, then I can use that in some way. It also makes it easier here where if I push this, I've like moved this transfer descriptor, but now I can like get him back with some packet ID stuff somehow. Maybe. That seems kind of reasonable to me for now, but I'm like very unsure about that. So maybe this is one of those like we save it till we need it kind of things. But I think we do need it now because we need to reference the like stored version of the buffer. No, I think we don't. So let's, if we instead do this is box new transfer descriptor. And here we say read TD storage is this. Then we can get the pointer to the storage right now. It's just tricky. It's all tricky. We say let store read TD pointer is read TD storage.descriptor as mute transfer descriptor. Hello, how's it going? And then we can push the storage to our like vector. So we do TD's push read TD storage. Having brain aches. Yeah, dude. Me too. Me too. So can we pull this guy out like this? Does he still get mad? No, because this is actually a borrowed thing, but if I convert this to read TD pointer, does it allow that? That seems okay. This guy I make mutable, and does it allow that? Generally, yes, except for the read packet is still being referenced here, so we'll pull that here. And then it's getting mad about like async shit being used across awaits. So this is all just getting kind of complex, which sucks. Really, probably what I want is like a way to like start chaining functions together. Like we could make a function that's like generate read packet, or maybe we'll call it like generate input TD. That seems pretty reasonable. And he returns a like ID of that guy, probably, and then I can use those to like stitch them together, is what I'm thinking. I would like I want like my get descriptor to say let read TD is equal to generate in TD, and I pass in like the stuff I care about, like the size, and like I would pass in like 18 bytes here, and like the address, so 0, and the endpoint probably, so also 0. Right, I'm like reading from this address, this endpoint of like this many bytes. Right, so here then I would want like address is a U8, endpoint is a U8, and size is a like U size. And then I would want to be able to say like let setup packet is equal generate setup TD, and it would also go to that address and endpoint. But maybe here I would like inject the packet. So here I would like say setup TD is this guy, and maybe I like shove in the setup packet. And then what I would also want is I would want to be able to like say setup TD set link to read TD. Right, like that's kind of like an interface that would work well. Then I could start like, if I wanted to make like chains of actions, then I could easily queue them up together and then push them into a queue. So then there's like, we would have to get a little careful with these interfaces. Here we would want to return like something related to something like a type that will automatically clean himself up when he's dropped, as well as have some like things on him. So maybe we'll call this like a transfer descriptor. I don't really know what the right word for this is. Right? Like it's not a transfer descriptor. So the transfer descriptor is the thing that we're giving to the UHCI card, but maybe something like a transfer descriptor handle is like an appropriate name for what we're doing here. So we were like, here's a handle to the thing that we've stored. That seems reasonable. I'm also realizing that in my list of things that were worked on, at some point in time, we started working on interface cleanup for what do we want to call this? Queuing TDs. Okay. So what does this transfer descriptor handle look like? Transfer descriptor handle. So he's got a reference to this guy probably. So I wonder for now, maybe we can get away with him being like holding on to him to self. But I don't think so, because I think these transfer descriptor handles will probably like end up around the system. So probably what makes sense is for them to be behind some sort of like shared reference, which means that it also makes sense for them to be behind like some sort of mutex. So we've got this very, very sick arc mutex. This is no longer a vec, this is a hash map of the TD ID, transfer descriptor ID, to transfer descriptor storage. Which means that we probably want like a transfer descriptor ID type that's just like wraps a usize, but just makes it clear when I have like my type system tell me what the types are. And this guy needs to derive debug and hash, or else it can't be used there. We need to import our mutex type. So here we've got a mutex, an async mutex that we've written before. So we'll just say util, we pull in mutex, and I think we're chilling. There's like a bunch of compilers down here somewhere that I just need to smack out real quick. For now, we'll just comment out this whole get descriptor function. And we'll just make sure that everything else is still compiling. So this guy, he needs unimplemented, or else he'll get angry. And we'll just cargo check to make sure that we're like in a compiling state. So we're close. We just have to populate these things that we have. So we have let queues equal to vec new, and let TDs is equal to arc new, mutex new, hash map new, TDs and queues. Cool. So now do we at least compile? I want to stay in like a compiling state so I can make sure that all the stuff that I'm doing is like working as I go. So now what's going in our transfer descriptor handle? We have, let's think. We have our ID, and we definitely have a reference to this like transfer descriptors thing. So we'll say what? We'll like make a type alias for this because it's like fucked. So we'll make this like shared transfer descriptor storage or something. Yeah, sure, fuck it. And this is this shit show of a type. Here we say TDs is a shared transfer descriptor storage. That looks a little nicer on the eyes. And so we need to say, well, I was going to say that when we drop this handle, we should remove it from the storage. But that's actually not true. Because we have two users of this guy. One is the hardware, and two is whoever cares about him. So how do we want to structure that? Probably it makes sense for the how do I say this? Maybe the handle, maybe he doesn't have this like shared storage in him. Maybe he has like just the buffer. So like arc vec u8, right? The buffer that he's trying to work with, because the person who's using these guys maybe doesn't care about the transfer descriptor himself. I guess he also has to care about like linking them together still. So he does need to be able to access the transfer descriptor that the hardware is seeing. Okay. And so what else does he need to do? Let's go back to where I was using this guy and see what I wanted him to do. I wanted to be able to generate a transfer descriptor that has a way for me to like set up links and a way for me to look at the data. So maybe this is silly. Maybe we can actually like ditch this whole concept. We just go back to a vec box transfer descriptor storage here. Maybe. And maybe here, we just make sure that these guys return boxes of these to transfer descriptor, or this guy returns like box transfer descriptor storage. That seems kind of reasonable. So here, if we generate our setup TD, he takes in an address, an endpoint, and a packet, which is a vector U8. And maybe arc, a shared reference to a U8 slice might make more sense. I'll think about that in a minute. But for now, he'll pass in like a vector. And so then this stuff should compile. Like this. And we can pull out this guy that does the setup stuff. And he'll say, let return is a box new, transfer descriptor storage new. I guess he doesn't have a new function. He's just got like a direct thing. The buff is going to be the packet. And the descriptor is the transfer descriptor that is just 8 bytes of 8 words. Now I can do all of this stuff on this guy. So I can say ret.this. Sorry. For all of these guys, I say ret.descriptor. And then I return red. And the data here, I just set to ret buff dot as mute pointer. Yeah. This is starting to look good. So he can't bar this as mutable, which is weird because I just forgot to write mute here. Cool. And so now I can say, here we have a setup packet. We generate the setup TD. Then we say our read TD is going to be generate in TD. Oops, here we have to set the address to the address and the endpoint to the endpoint. The maximum length have to be packet.len, I guess. And we will actually do a try into, because somebody could like, you could see somebody putting in a packet that's too big. Now the question is are these packets ever going to be generated at runtime? Are they all going to be generated at compile time? Because if you could argue that it's a programmer error if they don't work, and it could be an assertion instead of a returned failure, but I'm okay with the return failure for now. So we'll say result, and we'll call this what? Invalid packet error for now. And somewhere we're gonna have to say like pub struct invalid packet error, and he like implements debug. Yeah, sure, fuck it. So then we just say, if this fails, we'll map error to invalid packet error. Okay. Are we chilling? Borrow of move value packets. So we just say ret.buff.len instead. I don't know if this is correct, this max length. I don't know if we're supposed to set it if it's an output packet, but let's maybe take a look. Probably we should, because otherwise how does the descriptor know that it's allowed to access that data? Sure. So now we generate our read TD. And this also goes to address 0, endpoint 0 with a size of 18. And here we say set of TD. And what is his descriptor? And set. Oh, this isn't an async function. Oops. So we'll just do that. No field descriptor on this guy. So we have to expect invalid setup packet. And then we say descriptor. We want to set the link. So this guy is going to point to link pointer. That's a transfer descriptor. And it's going to be read td.descriptor. Oops, this also has to be... Oh, no, this is fine. Descriptor. Probably we need to do like something like this. As mute transfer descriptor. They're okay with const here, so I'll just do that. And this is also not supposed to be an async function. All right, so that looks like the interface kind of makes sense, right? We like generate these descriptors in order, and then we like link them together before queuing them for transfer. And at this point, if we dropped these, if we just like returned and we dropped all these from memory, nothing bad would happen because the hardware doesn't even know these descriptors exist yet. So I think that that makes sense. Let's figure out how to make this like read descriptor here. So he's going to say our buffer is going to be the size they pass in. We're going to say the return value is the same here as what we did here. We did box new, transfer descriptor storage, blah, blah, blah. And then we just have to set up all these values. So set the status to 0x80, set low speed true. We're going to have to deal with that later, but I don't want to right now. The link pointer, we don't have to set. But probably we should initialize it by default to none, actually, now that I think about it. That actually makes sense. Otherwise, how will we know? Like, if nobody else sets it, we should make sure that it's in a good default state. And what goes in here? Ret descriptor. Descriptor. Oops. And then we return ret. Cool. I guess our size should be a U16, actually, for these. Which means that this can be size as usize, and then we can just set size here. Is there anything else in here? Address needs to be the address. Endpoint needs to be the endpoint. And the data needs to be ret.left as mute pointer. Cool. So now we've got our generator, our setup to transfer descriptor. We've generated our read transfer descriptor. We've linked them together, which means that all of this code can go away, but this queue head code can stay in. When we generate our queue, we set the first value to the setup TD. So we say setup TD dot. I already forgot descriptor. Oh, oops. Let setup TD is this dot expect invalid setup packet. Now this guy's the right type. In multiple places, cannot borrow as mutable because I need to write mute here. That's fine. Otherwise, it looks like this works. And I guess, can we just uncomment all of this and see if we still get the value? So this would be read packet read td buff. Yeah, okay, we're close. Okay, so if I run this now, I think that should compile. No, fuck. 290. So he doesn't like this because it should be a vector new. I forget what type this is. Vec box transfer descriptor storage. This would be vec new, like this. Easy. Does this build? This builds? Maybe. Compiles, runs. And do we get a TD? Do we get like our descriptor out? Yeah, okay, cool. So that's like a lot of cleanup that resulted in a device descriptor that still reads correctly. So that's cool. So we'll just checkpoint starting to clean up. Now the last piece here is that we need to store our queues as well so that we don't have to do this like tracking of like, because right now our queue is in our stack, and so we can't actually leave this function until the USB card has finished running the queue. Everything else is on the heap, so as long as we store it somewhere, it'll work. And probably what we want to do is maybe we initialize our, for now, we look at this USB card. The USB card is iterating over all of these guys in his list one by one, once per millisecond. And they are all go, hey, I have some work that I want to do at this point in time. For now, we'll just say every single element in here points to like one static queue. Then we can just like punch shit onto that queue and it'll stay valid forever. Now the question is, how do we like append work to one of these queues? And probably, I think what I'm going to do is they have these things called like, they have vertical and horizontal transitions, I guess is what they're called. So you have like Q1 who points horizontally to Q2, points horizontally to Q3. These, if this points down to like transfer descriptor, things that point down are like auto incremented and things that point sideways are not. And so I was going to say like I could like punch in new chunks of work sideways here, but it doesn't actually work like that. Probably what I want to do is I want to say in my initial queue, I will point downwards to Q2, which is like, or Qn I should say, which is like a chunk of work that I want to do. For example, the get descriptor is three transfer descriptors. It's this setup, data, and ACK. So I could like package all of these guys up into a queue and append this queue to the queue of queues. Which means in order to do that, I would have to like walk down the list and just stick it at the back, right? I have like Q and 2, oopsies, Q and 3. And what I basically do is I just like walk down this list and like at the last guy, stick in Q and 4, which is my guy. That seems reasonable. So the first thing to do is to like set up a static queue. So we'll say what our like frame, our queue is a oops, this doesn't go here. Sorry, this goes here. So we'll say master queue is a queue head. And I guess we should make it a box queue head so that make sure it's like stuck in a static location memory. And we'll make a function on our UHCI that says append work. And this will take in my self-immutable reference as well as a link pointer. Is that correct? No. He's going to take in a queue head. That seems more reasonable. No. Fuck. Okay, so in the same way that I have this like transfer descriptor storage that wraps like the transfer descriptor along with its associated data, I should probably also have like queue storage. And he will have a queue, which is a queue head, and also buffs, which is a vector of transfer descriptors. Right, so the idea is maybe I can like append a queue. This queue head has all of these transfer descriptors inside that have their buffers associated with them. And if I drop this queue, then I drop all of this associated storage with all of the transfer descriptors inside. And I wonder if that makes sense. I wonder. Let's think about it. I guess we can just start implementing it and seeing what it looks like, and that'll like clear it up real quick. So in the same way that we have these like generate setup TDs, we might want to say like pub function generate queue. And he takes in a vector of transfer descriptors. So we'll say TDs is this. And he could return a queue head's queue storage. And he could actually handle the like linking together. So he could say for TD in mute TDs, we'll say TD, or I guess we'll actually want like windows of this guy. So we'll say TDs, tidders. Why am I saying tidders? TDs dot intermute dot windows or chunks. I thought there was like a way to like get like pairs of items together. Which is called what? Windows? Ah, that's only on a slice. I see. Which says iterator over overlapping subslices of length size. Which comes from slice windows. Right, so this is what I want. I want like RU followed by U as perfect. Perfect. So here I say tds.windows2. For window in tds windows 2. So I have window 0 is the first thing. Let first is equal to this. Let second is equal to window 1. Let's put references here so there's no copies. And I guess I want mute here. We'll say that the rest of this is unimplemented so that we get no type errors. And we'll say what? First descriptor, set link pointer. The pointer set link pointer is going to be set to second dot descriptor. And we're going to say link pointer td this guy as const t transfer descriptor like this. Cool. So this sets up all like this links them all together. And then we can say let queue head is a queue head new, or we don't say new, we just say 02 here. It's for 2 words. We can just make this mutable probably, and we'll say queue head set element link is just going to be to the first guy. So we're going to say link pointer td, and we're just going to take the first thing. So we're going to say td's 0, or td's 0 first, I guess. Yeah, we'll just say 0 here. Descriptor as const transfer descriptor. Okay, so we have our queue head, we have our transfer descriptors, and so now I just guess we just say box let we just return our boxed storage, I guess. Is that correct? Yeah. So that we know that it has a static area spot in memory that we can pass to the USB card. You say box new. Queue storage. And he needs a queue, which is his queue head. And what else does he need? He's missing buffs, which is our TDs. These actually also have to be boxed here, which means that this guy needs to have boxed transfer descriptors like this. But other than that, I think that compiles. Missing something called master queue. I guess we just don't need that yet. He doesn't like this Windows thing, so I probably need like Windows mute is probably a function that exists. No? Is there no mute? There's no Windows mute? No way. Rust Windows mute. It's a technical limitation. It's impossible to express in Rust? Are you serious? Alright. Fuck. So we'll just do it manually. We'll say, for I in 1 TD, in the range of 1 to TD's length, we'll say that the first thing is TD's I minus 1, and the second thing is TD's I. Oh, I can't. I see. So we say let second pointer is TD's I dot descriptor as const transfer descriptor. And then we say first is this, and then we say first dot descriptor, set this as second pointer. I think that works out. Cannot borrow TDs as mutable. It's not declared as mutable, so we just throw this guy here. And otherwise, I think that looks like it's compiling. Cargo check. Cool. And so now we have like this queue that we can now push. Cool. And does this queue storage make sense? We have a boxed queue head with buffers that's associated with. I think that could work. So here, let's comment all this out and see what it looks like if we say let queue is equal to. Oh, I guess we do need to set the head link to none as well. Make sure it's initialized correctly. So here we say self generate queue. And we say vec read TD setup TD followed by read TD. Okay. Cool. And so we have our queue here, and we can run the rest here where we do the same thing that we were doing before, where we like take all of the elements in our frame list, point them all to this queue that we just made. So we put this to queue. This is a box queue storage, so this needs to be queue head, I think. No field queue head on that guy. What is the correct name? Queue.queue. All right. All right, and then we just need to fix some of our logs here. These guys are not mutable references. And And now how do we like get the data out? We have, interesting. We've lost the storage to our input buffer, right? So we have this like read TD inside, and we like know what it is. But then when we push him into the queue, he now is like just like a buffer, one of the many things that we're doing here. Maybe it makes sense for us to like know that he's in the queue in that spot. So we could say we look at queue buffs 1 dot buff. Like maybe that's okay. Interestingly, we can't borrow him as mutable anymore, I guess because the queue is not mutable. And here now we just say instead of that we're doing queue buffs 1 buff. Okay, so that all compiles. And if we run, do we still see the right answer? We do see a descriptor with like a vendor ID and product ID, still what we expect from the mouse, so that's good. And now I guess the only question is, how do we like dispatch this into the global queue of stuff to do? So here our UHCI guy, he's going to have like a master queue, and he's going to have a queue head, maybe a queue storage. And maybe this queue storage can either take in a list of, like, it can either be a pointer to queues or to vectors or to transfer descriptors, right? Because like the queues can point to queues. So we could say that this takes in a T and this is a T. And maybe when we our master queue, let's see, where this guy could maybe put in he is a queue storage of queue storages to transfer descriptors. Maybe, right? So like the first layer is always going to be chunks of work, and the second layer will always be single items. And then maybe here when we generate a queue, we generate a queue with transfer descriptor storage. Maybe. That seems kind of reasonable. And then, now what? So we make our master queue. And what is he again? He is just a queue storage with buffs empty list of buffers, and his queue, he needs a queue that he points to. So probably our like default state is that our let master queue head is going to be a queue head of these USB guys, whose default initialized to 0, 2. And we'll just say master queue head set element link to link pointer none, and set the head link to link pointer none. So he's just like an empty thing. Nothing's going to happen when we look at this guy. And now we can say that our master queue is a queue with nothing to do. This guy also needs to be in heap allocated memory because we're going to pass him to our UHCI card, and so we just need to make sure that he's in a static location, right? Because like if we moved our driver around, we wouldn't want the memory that the USB card is pointing to also moving around. And now what we can do is when we like initialize our frame list, which is like the thing that the USB card looks at, instead of it always having nothing in it, like it does here, we could have it point to our master queue. So we can say set link pointer at the element for each element in the list is going to go to link pointer q head, and this is going to be master q as const q head. Yeah, this needs to be borrowed. And this needs to say mute here. Okay. So now I think we're in a state where we could append work, which is a queue head of transfer descriptors. Yeah. So what does he do? First, he makes sure that we store, how do I say this? We need to make sure that we store the buffers long enough for hardware to deal with them. So he takes ownership of the work. And then the question becomes, how do we get that work back to our friends? So that means that these like other storage, we don't care about these anymore. The only storage that we're gonna have is queues of work. And so we're gonna say self master queue dot buffs dot push the work, which means that this is to be boxed. He doesn't like this. Why? Buffs is a queue storage. Cargo check. Maybe the cargo check will tell me. He expected this, but I got this. Right, so I was supposed to write here my master queue. This should have said storage here. Okay. So there's some like mutability problems here. So 285. He doesn't like this because I didn't write mute here. This guy doesn't need to write mute here. But otherwise he compiles. Okay, so what we're gonna do is we're gonna append the work, but we also need to put that thing on the queue. So what we can do is first we should stop the card from running probably, because the card is like doing stuff. And it might be like traversing the list as we go. So maybe we say self. I'll just write fix me. Stop the card from running while we push. Then we say, we look at our master queue and we say, where are you pointing? So we can look at the queue and we can look at the element link. We can say, where the fuck are you? So we can say let link pointer is equal to this. And then we can say, we'll do like an endless loop here, and we will look at the link pointer. If the link pointer is none, we're done. If the link pointer is a queue head, so we look at the head, we check its element pointer, and we assign that to the link pointer. Right, we say like keep iterating down here. If the link pointer is a transfer descriptor, we do the same thing. Link pointer is the head.element link. All of this can go in unsafe. And this doesn't have an element link. He has a link pointer. Now, link pointer is actually a problem here. We need to set sorry, let me think. So what we're trying to do is we're trying to set the last element in this. We're just trying to point him to our work. So let's think about this. I need to draw it out. My head hurts. So we have, this is what we're trying to do. We have frame pointer goes to Q1. And each of these guys points down to a next Q. But this is actually not true. Probably. Right, because if I point down here to another Q, if I just pointed down like this, I would never actually do, there's no transfer descriptors associated with this guy. So really it has to be more like, sorry, brain's melting. Do I have to point sideways to Qs and down to transfer descriptors? That would make sense, because then I would have like all of the batches of work. Or maybe how this actually works is each Q, the last thing that they point to points to another Q. So you could have like this. This guy points to TD, points to TD, and this could point to QN2. And he could point to TD. He could point to a transfer descriptor. That makes sense. So it's just like a chain of work. But then the question becomes like, why do these Qs exist at all? Right? Like, does it make sense for it to just only be transfer descriptors? Right? Because like now this Q kind of has no purpose. I think that's correct. So instead of passing around Qs, I can pass around like batches of transfer descriptors, and that will probably work out cleaner. Okay, so this Q storage is always going to be storing transfer descriptors, so we just nuke this. So this just goes, master Q is a box Q storage. Great. Now when I append work, I take in I only take in a vector of transfer descriptor storage. Okay. And these transfer descriptor storage have to be linked together. So where we were looking at Qs, which was here, generate Q, we should instead say link TDs. And this will just take in a mutable slice of these guys. Right, we don't need these anymore. So we don't need to create a queue here at all. And this just links all of these TDs into a chain. So now we can say that our descriptors, our work, is equal to this vector of work to do. But then we need to link them. So we just say self chain TDs mute work. Then we say self append work. Work. Is that correct? That seems right. But he actually doesn't like this for some reason. Why? Because this is a vec box transfer descriptor storage, and this guy says vec transfer descriptor storage, so we'll just put a box here. Oops. So now, I guess in our scenario now, all of our work is just sequential, right? Right. Oops, sorry. I just had my stream open in the other window and I accidentally hit play on it. So if all of my work is sequential, I just have to go to the last element in here. So I say, if let sum work why isn't it like this? Oh, if let sum td is equal to this, we say td dot descriptor set link pointer, and we just set it to the first thing in our work. That makes sense. So we say work 0 dot descriptor and we say as const transfer descriptor. That seems reasonable. This needs to be a link pointer, so we need to say link pointer td. Okay, I think we probably have to last mute here because we're mutating it. Otherwise, say self master q dot q set element link to this guy. And then we say self.master q.extend or buffs extend work. I think that's it. We also will have to check if this has already been completed. So we say if td dot, how do I do this? td descriptor status and 0x80 as the are we running? If this equals 0, i.e. we've already completed this, we set the element link in the master queue, else we do it at the end of this guy. Let's go, baby. That looks right. That looks right to me. Okay. Now the question becomes, how the fuck do we keep track of our buffer now? Right, because here we have like a buffer that's of eq8, but we've lost track. We've given it off to the system. So maybe instead of a box here, we actually use an arc, right? Because then we can actually keep handles to our transfer descriptors, even though they've been dispatched, and everything else should work the same. So here, everywhere we have box of transfer descriptor storage, we'll just return that. We'll replace that with an arc. Which I think makes everything make sense. Which means this would be arc new. This also has to be arc new. Is anything else failing to compile? Almost certainly. 536. What isn't it like here? Oh, all of this stuff is fucked, but that's okay. So we'll comment this out for now. Oops. 527, he doesn't like this because it's immutable. Everything else, though, he doesn't like this thing at line 522. Cannot borrow. Oh, fuck. But the stuff in the arc is not mutable. But that's okay. This works out. But this stuff does not. So how do I want to handle this? I can't have it as shared references at this point, I guess. So this needs to be boxed. This needs to be boxed. This needs to be boxed, and we convert them into arcs later. Probably. Thinking about that. Meep moop, meep moop. Running the simulations. But I think that's going to be a problem too, because when we append work... Oh, yeah. No, we could do this. So we could have it be boxes everywhere until we append work. Then what we can do is we can return a vector of arcs. So we can say, now that we've pushed it in, you get this shit back, but they're shared references now. And so we can say work is equal to work into iter map value into item into. And I think that should just automatically convert boxes to vectors. And then the only place I need to make these arcs is here in my queue storage. And obviously it's bitchin'. But I think most of that's around here, around this queue stuff that's wrong now. Cargo check. Okay, we're close. We have these like mutability fixes that we still have to make that we made before. So this is mutable. We don't need to make this link pointer manually anymore. These don't need to be mutable. And I think we're close. 298. All we have to do here is return the work. I think. Can I make like an arc from the box? Oh, you need to collect this as well. Oops. So work is a vec of arc transfer descriptor storage. And here I can clone the vector into an arc. There we go, baby. I guess I can probably even write work iter clone. Yeah. So we're very close. Other than 304, what isn't it like there? Cannot borrow data in arc as mutable. Oh, we still have this problem where when we alter the very last guy in the list, he's mad that he's behind an arc. Oi, yoy. I wonder if we can get away with only the buffers themselves being arcs. I guess, you know what? Fuck it. What we're gonna do is these descriptors. Are just gonna be unsafe cells. And we'll deal with the consequences later. So that's gonna cause all sorts of problems. We need to use core, cell, unsafe cell. Like this, and then there's going to be a bunch of places where he doesn't like that. So that's in 304. Do I just call get? Oh, this doesn't work either. Fuck. Because that'll probably move. That'll probably move something. Ugh. We'll just fuck it up here. I'm gonna cheat because I don't know how to deal with this right now. But if I say td descriptor as const transfer descriptor, like this, and then I say let d equals D as mute transfer descriptor. We'll just fucking violate Rust guarantees. And we'll just say D.set, then we'll just call this on star D. This is broken as all hell. But that's okay. I'm pretty sure this will work anyway. But we'll see. Does everything else work? Yes. Okay, so now when I append this work, I can say work is equal to this guy. And then I can do my sleep for 2 seconds. And print out the work. So hopefully this all still lines up. Hopefully all of this still results in a descriptor that prints out what we want it to. Which it does. Perfect. So we are still in a state where we are printing out what we want, but we are now have something that's much more sane for an initial, for like something here, right? Now all we would have to do probably here, I'm actually going to call chain TDs on the work when I append it. Right? And then now this is looking like something that I could call somewhere else. Like this is looking like much more high level. And now I can like generate my packets, chain them together, append them here, and everything will just work. I hope. There's some like volatile writing and stuff that I've skipped that I will have to get to. But yeah, otherwise it's looking pretty good. We are at the 2-hour mark. I was trying to spend today looking at like, I wanted to make progress on talking to the mouse. And we haven't really actually done anything. All we've done is changed what the code looks like to get to the same result. However, I do believe that now when we start to talk to the mouse, it'll be much easier next stream to start like generating new transfer descriptors and chaining them together. Because now we've got to the point where we no longer have to worry about memory allocation issues, right? The card will always have some valid memory to talk to. Eventually, we are going to have to purge some of this work, right? So we're going to have to like make like a pub async function service. And he's going to have to like wait for TDs to finish, purge them from storage, right? But for now, we don't have to worry about that. Yeah. So I think that's cool. I'm happy with that. Yeah, I'm happy. So next stream, hopefully we're going to start actually trying to talk to the mouse. I was hoping that was this stream, but you know, it is what it is sometimes. If you liked what you saw, I stream most days around like 1 or 2 Pacific time on Twitch. If you're watching on Twitch and you missed stuff or you want to catch up, whatever, there's a YouTube link in the Twitch description. And if you're on YouTube and you want to catch me live, say hi, chat, whatever, there's a Twitch link in the YouTube description. And if you want to look at the source code, there's a GitHub link in the YouTube description. Or you can like browse GitHub and just look at like the same username that I have on Twitch and YouTube is the one that I'm going to have on GitHub. There's a Stream OS repo in there that you can look at. Otherwise, yeah, thanks for watching. I'll catch you on the next one. Bye!